pre-calc fans out there. We're going to be working on 3.5 for
That's right. You know who you are.
Video today. And let's see, zoom in a little bit here.
Yeah, thank you. It's hard to see being so old.
First, in an exponential equation like this, when you're solving, let me just kind of remind you, this is kind of the stuff we did.
Okay, now, as a word to you about what we just did, let me get my other writing tool on because I don't have it on right now. Okay, so when you are solving these, we have got to isolate this part of the equation. That's the exponential portion. That has to be isolated before we can ever start down the road of changing to log form. So, just thought I would pause and throw that in there. Okay, now, what else was I saying?
Back in Algebra 2, get something like this going on. This would be something I would not need a calculator for.
Yeah, that's true.
Because both sides are based on the whole number 2.
Yeah. I don't know if they'll see that.
This is an ICE learning day, so I am recording a video in the minivan of my car. In the
You
garage.
are? Oh, that is so cool. You're in the garage.
Nobody's awake at the moment. And my dog is next to me in the car.
Hey, Bodie.
Because I didn't want him to make much noise in the house.
That's right.
Anyway.
And he would too, folks.
Hopefully he won't be a disruption to us.
No, yeah.
Okay. So, they have a common base of 2, so we've got 2 to the negative first. And we have, everybody should know that that's 1 over 2 squared, which would be the same thing as 2 to the negative second.
Okay. Now, that's one thing I think that you guys struggle with is realizing that you need to rewrite on both sides there. You have to think, okay, how do I think in terms of rewriting this with a common base, and everything's based on 2, and to get that to flip over, you have got to do that 2 to the negative first, and to get this to flip over, you've got to do 2 to the negative second. So, I think I kind of went through that fast, but you got to, I mean, those are Algebra 2 concepts, so that's kind of why we're just cruising through things, but that's something we should be reminding ourselves of. Okay, let me undo that. Oops, let me clear that. And resume. Maybe. Hopefully.
Okay, and what can we do with those exponents? We can multiply them. So we have 2 to the negative x over 3 equals 2 to the negative second. And that means if the left side is equal to the right side and the bases are the same, then that means that these exponents are also the same. Negative x over 3 equals negative 2.
So, I mean, that's the goal, is to get that common base like we talked about before. And I know it seems like I'm going through this really quickly because I know we've been doing a lot of review of this in the past. And it is a review topic from last year, so that's why I think I'm going through it quickly. But if you need to pause and just kind of digest it, that's what's going on here. Is we're just rewriting to a common base and then analyzing those exponents and saying, okay, these exponents have to be equal, and if they're equal, then we can solve that and get x by itself, which is what I think I'm about to do. I mean, that's what I imagine I'm going to do. Let's listen to myself.
Multiply everything by negative 3.
Amen.
And we get x equals 6.
Good job.
So, didn't need a machine for that one.
Nope. No machine.
If we made them uglier than that.
In fact, we are the machine.
Yes, we would need a machine. You're right. Okay, so let's see here. Okay, now this one's kind of a different one.
Why is this dude yawning so much? It's gonna make me sleepy. I know. He recorded it in the morning on an icy day last year in the minivan. Sounds like a game of Clue, but this is a quadratic. Now, I know you don't know that right now, but this is a quadratic, and we eventually are going to be using the quadratic formula. So hang on to your hats, but eventually we're going to be getting to the quadratic formula on this question. What's he doing now?
Okay, so get up here. Get over.
Come on, dog. Stop messing up the video.
I'm not sure this is gonna work. He might have to go back in his cage.
Yep, Bodie. Get kicked out of the van.
All right, now. So a lot of you probably would want to multiply by 2 on both sides. That's not a bad idea. You have e to the x minus e to the negative x equals 10. Okay, this is where it kind of gets a little weird. What you're trying to do, or a little different I should say, what you're trying to do is turn that into a constant value. And so what we're going to do...
Stop yawning.
I know this is a little weird.
Don't you do that to me.
You probably have never done this before. But, and I'll switch to a different color just for fun here. We're going to multiply this whole thing by e to the x.
Okay, now you need to start envisioning what's going to happen with this. Okay, because we're going to start distributing that e to the x. And like he said a few seconds ago, we're trying to turn the one that I circled there, e to the negative x, into a constant. And just reminding myself, when you multiply like bases, so when I multiply like bases, what do I do with the exponents? And I hope you said, add them! That's right. So 2 plus 3 makes 5. Okay? So when we're multiplying like bases, we're going to be adding the exponents. Okay? And hopefully that helps you as we go through the rest of this question. Let me clear that out.
Now, when you distribute this to this, remember when you multiply like bases, what do you do with the exponents? You add them together, right? So that would be...
Okay, now just quick question. What's x plus x? That's what we're... Oops, stop moving. X plus x. We're adding these two things together, right? That's where this 2x is coming from. Okay, not x squared, right? 2x.
It's a 2x. And when you add the exponents together on the next one, x and negative x,
what do you get to? X plus negative x. X plus negative x. Wouldn't that be 0? So we're really going to have e to the 0 power, and we all know that is equal to, don't say 0, please don't say 0, please don't say 0.
Cancel out, so that becomes e to the 0. Well, what is e to the 0? We know that e to the 0 is 1.
Amen.
So that's a constant value, and then we have 10 to the e, or 10 times e to the x, when we finally do the last part. Okay.
Now, I know at this point of this problem, you do not see a quadratic. All right? Now, I would like to show you what you have basically, all right? Currently, if you kind of want to look at this, this right here is like having x squared. Okay? This right here is like having a minus 1. And then pretty soon we're going to take this to the other side, and that's like having and if we brought it to the other side, it would be negative 10x. So this is kind of the idea of what we're getting at here, and maybe you'll see that here in a second. Each one of these x's, that problem right there at the top of the screen is something you'd see in Algebra 2, and of course you'd hit it with the quadratic formula. So this right here is a version of a quadratic, and we're going to use the quadratic formula. There's going to be a minor change to the quadratic formula that causes more work. Okay, not a tremendous amount of work, so stop complaining. Okay, I better hit the play button, otherwise I won't hear myself and I'll be sitting here for a while.
Okay, so let's say we put it all on the same side.
Don't yawn. Keep your yawns to yourself.
We have e to the 2x minus 10e to the x minus 1 equals 0. Now, we've talked about something similar to this in Algebra 2, but what you're looking at right now is really a quadratic. Right? Now, you might say, well, I don't see how it looks like a quadratic. Well, it's e to the x squared minus 10e to the x minus 1. So, right there we have our quadratic. And to solve a quadratic,
nope, don't yawn.
there's two different ways we can
Get some
handle this.
coffee,
We can handle
dude.
this graphically.
Get some coffee.
Like,
We're not graphing
jump
this.
over to Desmos here.
Oh,
and
please
type
don't tell me
this
we're
in.
going to graph this.
Do that.
We could. Okay, all right, we're going to graph it. Seriously.
Why?
Why don't we just use the quadratic formula? I mean, this will be useful for you to see, but...
X parentheses.
Yeah, back that up. Use that. Okay, there we go.
Squared. That is 10e to x. And minus 1.
Okay, is he going to get there eventually? Okay, better change the window.
Okay, that's looking a little weird. Let's see if we can find...
Zoom in.
Zoom in on the home here.
Weird.
Whoa, that's really looking weird.
It is. I have to agree with you. Wholeheartedly. Whoa, man. There's only one place where it crosses the x-axis.
Sorry.
Yeah, stop moving it around.
It's a bizarre looking graph. But the answer to our question is right there, 2.312. Now,
Okay.
that's how we do it graphically, right? Because we're setting it equal to 0 and solving.
Don't do it. Don't.
But how do we do that
Oh, my
algebraically?
goodness. Keep your mouth shut when you're yawning.
That's where is it? Okay, so algebraically, I'm going to have to use the quadratic formula.
Finally.
Now you're saying, okay, how do you use the quadratic formula for this? Well, you know your coefficients, right? We got a 1, and we got a negative 10, and we've got a negative 1. The difference here is, instead of being x on the left side, it's e to the x.
Okay, that's a big difference right there. I'm going to pause it for a second. You have to understand that, okay? We're talking about the quadratic formula, and I know you guys are used to, let's see, I'll just do this quickly. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's what you're used to. But instead of having x over here, we've got e to the x, which means that's going to add a layer of work. Not tremendously. Now, before we get too far, everybody knows what e to the x looks like. You should know. It's exponential growth. And everybody should know that exponential growth looks like this. Well, what do you know about every exponential growth? What do you know about the range of an exponential growth function? Well, the range goes from 0 to infinity. When is it ever equal to a negative number? It is not equal to a negative number, nor will it ever be. So you need to understand eventually that there will not be any answer used in the next step after the quadratic formula gets processed. We will have no values for e to the x which are negative. We can't have a value that's negative. Now, if the quadratic formula spits out two positive numbers, then I'm going to have to process both of them. But based on the graph I just saw a few seconds ago, where there was only one answer, I'm pretty sure that the other answer must get tossed by the time I get to the end of this question. So, well, let's see what happens as we keep going on our journey to the center of the Earth. The center of the exponential growth function. Okay, next.
Was it a b plus or minus the square root of b squared squared? I'm going to run out of room. I might as well figure out my discriminant here.
Yeah, figure out your discriminant somewhere else.
And come back in there and do that. So b squared minus 4 times a times c.
Okay, now, do you understand that, and maybe you do, maybe you don't, so I'll just, in my mind, do you understand that you have a 1 for A, a negative 10 for B, and a negative 1 for C? You're using those coefficients, A, B, and C, in your quadratic formula. That's how we're getting this discriminant, which is what? 100 plus 4, 104? Something like that. I just thought I'd double check.
104.
Amen. I'm so good.
So we'd have 104 all over 2 times 1. Alright, so the interesting thing here is one of these is going to generate a positive, and one's going to generate a negative. The negative one will not work.
And that's exactly what we talked about. The negative one in this case will not work because the range of an exponential growth function can't be negative.
And I believe that would be with the minus.
Yes, it would be.
We really need to figure out what, so let me lock that in place. So e to the x equals, if we jump over to a handy dandy calculator, which I'm going to pause and find one. Alright, so
oh, look.
10 plus square root of 104. Okay. That value divided by 2. Alright, so now we got that. So that's 10 point. I think it was
099. Come on, 099.
I recall correctly.
Oh, man. He's taking forever.
Yep, 099.
It's because he's tired. It's just because he's tired,
Terrible
folks.
looking at. Alright, so how do we solve that?
Great question. How do we solve that? It's in exponential form, right? We've talked about how that, when you have everything in exponential form, something to the something power equals something, you've got to be prepared to change it to log form. And this is base E, so I really hope you know what kind of logarithm to use for base E. We shall see.
Yes, we need to change to logarithms. That's right. So we want the natural log of that answer. And in fact, because I don't want to, type that whole number in, I'm going to use the answer feature on the calculator, which will put that nasty number in there.
Okay.
Equals
Good
x.
idea.
And if we do that using our handy dandy calculator, the natural log of the answer, we get 2.312. Okay, so x equals 2.312. Like I said, the other one would be negative, and that wouldn't work. It's an extraneous solution. So that's the answer to our question. So there's the algebra and the graphing concepts for that.
Just keep in mind, sometimes there are more than one solution. Sometimes there's just one solution, but sometimes we do get two solutions.
Okay. Solve a logarithmic equation. So this is pretty basic. If you've got it in a log form and you want to change it to an exponential form.
What kind of log are we dealing with? A single log. You know what's about to happen, right? All the single logs, all the single logs, all the single logs, all the single logs. Oh, ooh, 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 ooh.
We do the same thing we did before. In this case, we're dealing with a common base. The base is 10. The exponent, remember logarithm means exponent.
All right, now remember, maybe I should have backed this up. I'll just let it go. We should at this point know how to change something from a log to its exponential form, right? We've talked about this enough. You've got to be able to identify these parts as you go through. Your base, your exponent. Remember, a logarithm means exponent. I'm trying to drill that into your brain because sometimes I'm wondering if it'll happen. Well, we'll see here. Let's go to the next part.
The value that it equals is x squared. So in other words, base exponent equals argument. And if you take the square root of both sides. Now, could it be positive 10 and negative 10? Would that work, children? I know that some of you...
Children? Who are you talking to? Okay, now, sometimes you're going to end up with, it's possible to have negatives. Don't sit there and say, as soon as you see a negative answer, say, oh, it can't be a negative. Sometimes you're right, it can't be a negative. You've got to go back to the original equation and figure that out.
Maybe we need to test this with the graphing calculator. Maybe we need to look at log x squared and see what happens.
Or Desmos, whichever.
Log x squared. Whoa.
That's
Take a look at that weird graph.
Man, it looks highly inappropriate.
That is definitely bizarre, okay? But, oh, come on. Where are you? Stop doing that. Click. There we go. Y equals x, y equals 2. There are two answers to the question. All right?
Okay, yep.
10 and negative 10. That's interesting because there's a vertical asymptote down the middle.
Oh my goodness, this is like the equation for a really poorly dressed plumber.
Is that right?
Yeah, there's a vertical asymptote because.
Yeah, it looks like the limit from both sides doesn't exist.
Yeah, nice. Yeah, it goes to negative infinity.
Negative infinity from both directions.
Whoa, it's like we think the same.
The overall limit at 0 doesn't exist.
Amen.
Whoa.
I know.
Little mean girls. The limit does not exist. Okay.
That's a weird reference, but yeah, I get the point.
Let's see. So, if I'm using my log properties here, because I see addition right there, I know I can multiply. So that would be the natural log of the product of 3x minus 2 and x minus 1. And I can also take that and make that an exponent based.
Now, why am I doing that? Because I need single logarithms on both sides of the equation. Single logs, right? That's what we want on both sides so we can compare the arguments.
On the move it property. So we now
That's right, because we like to.
If I foil these things together,
if you don't like the box,
you might want to shield your eyes.
Yeah, you don't want to look.
3x squared.
I like the box, really. I do.
Minus 2x and a positive 2. Well, it's a bad looking minus. Okay, so
yeah, kind
we
of.
have the natural log of 3x squared minus 5x.
Yes.
And a plus 2. Man, you're a loud snoring dog.
Bodie, are you snoring over there?
Yeah, we know if the
my
logarithms,
goodness.
if the bases of the logarithms are the same on both sides, then the arguments have to be equal.
Ooh, did you catch that? If the left side equals the right side and the bases are the same, the arguments have to be identical. Amen.
So we know that 3x squared minus 5x plus 2 is equal to x squared. Of course, we'll move this to the other side, giving us 2x squared minus 5x plus 2 equals 0. Wouldn't it be cool if that actually factored nicely? Let's check. B squared.
For those of you who don't remember, if the discriminant of the quadratic formula is a perfect square, then it does factor nicely.
Minus 4 times A times C. 25. Take away. Let's see, what is that?
16.
Hey, that's 9. That does factor nicely.
Yes, that's a perfect
Now,
square.
The bad thing about finding the discriminant and seeing that it's a perfect square, you're like halfway through the quadratic formula.
That's right.
You could just come over here and say, the opposite of b plus and minus the square root of 9 all over 2 times a. So sometimes, that little trick, if you can't do it really, even if you do it really fast, sometimes it's just easier to use the quadratic formula.
Yeah, we could have used the Berry method.
So let's see, 5 plus 3 over 4, that's going to give me 8 over 4, which is 2. So one of my answers is 2. And 5 minus 3, which is 2 over 4, would give me 1/2. Now, are those answers both good answers? You can come up to the original problem and plug them in and see what happens, right? So, right here, I would see, so let me lock that in, right here would be a problem for 1/2, right?
Yeah, definitely.
Because if I plugged in 1/2, then I would be taking the natural log of a negative number.
Now, why is that a big deal? Well, you and I both know that every log graph looks like this, okay? And what's the domain of the log graph? 0 to infinity, right? Where in the world is negative 1/2? Well, negative 1/2 is over here, and you're asking me what is the y value on that graph at negative 1/2 when there's nothing over there? Sorry for yelling in your ear. So yeah, that's a problem. So that 1/2 is not going to be a good solution for this. Because it creates a problem with that natural log function. Okay, clear, and there,
and we all know based on our logarithm.
Oh, is he going to graph it again?
Stuff like this.
Oh,
that
man.
The domain cannot handle a negative number.
Amen.
So 1/2 is not a good answer.
Right.
2 would be a good answer, but 1/2 would not. So we just eliminated one of our. Just eliminated one of our answers.
Gone.
So 2 is the only answer to the question.
2.
Now this topic comes up called orders of magnitude. It's nothing, nothing fancy.
No, not really.
So I put this paragraph in here so you could just see, they've got, planet Mercury is this many meters from the sun, but Pluto
Who measured
is this
that
many
with a
meters
stick?
from the sun. Okay, roughly 100 times farther. So when you write it out in scientific notation, you got 5.79 times 10 to the 10th and 5.9 times 10 to the 12th, okay? If you were to divide them, what they're looking at is the orders of magnitude would be, 10 to the 12th over 10 to the 10th, okay? And so when they say orders of magnitude,
remember, you divide like bases, you subtract the exponents. I know some of you are wondering where that came from.
they are referring to this exponent difference, right? Because when you're dividing like bases, you subtract the exponent.
Exactly, I just said that.
So 12 minus 10 gives me 10 to the second. Then the order of magnitude would be 2.
I'm not going to ask you an order of magnitude question on the test, but that's what it is. So if you see it in the book, if you have friends that you're talking to at a party and they refer to the order of magnitude, it's just the difference in those exponents. And in this case, it would be a 2. It does show up a little bit when we start thinking in terms of how much larger earthquakes are, kind of. We talk about it slightly differently, but anyway.
Okay, so that's really what they're getting at, is taking the difference in the exponents. Here's an example, the Richter scale example. It's a logarithm formula. A represents the amplitude in micrometers of the vertical ground motion at the receiving station. T is the period of the associated seismic wave in seconds, and B accounts for the weakening of the seismic wave with increasing distance from the epicenter of the earthquake. Okay?
It's a mouthful.
Basically, you have a shifted log function.
Shifted log function?
That's
Holy
really what we're getting
cow.
at here. Now, do you have to memorize that equation? Absolutely not.
Heck no.
Okay, that's not the point. So, if I'm going to try to compare earthquakes, how many times more severe was the 2001 earthquake than the 1999 earthquake? Okay, you really can look at these. These are exponents, right? Logarithms are exponents. So, really, it's like saying 10 to the 7.9 over 10 to the 5.9. Okay?
So, Richter scale values are not linear. Now, what does that mean to me? Well, if you see a temperature change outside of 2 degrees, none of us is gonna think that's a big change in temperature. But a change in 2 units on the Richter scale, that's a big deal, because those are exponents on 10. So changing that Richter scale number is huge. Not so with a linear scale. I mean, linear scales like weight and height, or length, things like that, their temperature, they're not the same, and you don't notice. I'm sorry, I'm yawning. It's the middle of the afternoon. Seriously. Okay.
Well, that's, we said we could subtract those exponents.
Do it.
And when we do, we get 10 squared. So in other words, it was 100 times more intense than the other earthquake.
That's pretty strong.
Okay.
Compared to the other one.
Quite a significant difference, even
Amen.
though it's only, 2 different on the Richter scale. It's not like a linear scale. Like if the temperature outside goes up by 2 degrees, you're not even going to really notice very much. But on the Richter scale, if it goes up 2 units on the Richter scale,
okay,
that's 100 times stronger. Sorry for yawning.
Yeah, I know. Man, I yawned again? Gee whiz.
In the morning. Okay, let's see here. Chemistry has their own other, problems to work on. The pH, the
No, you don't have to
hydrogen
memorize
ion
that formula either.
as it compares to the pH of that particular liquid. And you can see that it is a reflected log function. So when you're dealing with, let's see, some especially sour vinegar has a pH 2.4, and a box of leg and sickle baking soda. Never heard of it.
Leg and sickle baking soda. Is there a joke there? Leg and sickle. Leg and sickle soda. LSBS. LSBS. Leg and sickle. All right, I'm not figuring this joke out. If there's a joke there, that's just a weird name.
has a pH of 8.4. What are the hydrogen ion concentrations? Well, we'll do one of them here. So 2.4 equals negative log of the H plus. So I got to divide by -1 on both sides. So now I have negative 2.4 equals.
Now, why am I doing that? I'm isolating. Okay. I'm isolating the log function, getting it to be a single logarithm so that I can change it to its exponential form. That's what I'm trying to do here. Oh, stop writing. I'm trying to get this thing moving in the right direction.
That's terrible. Yeah, let's try that again. 2.4 equals log of the hydrogen ion concentration. And so we can change that to its other form, right? The base is 10, the exponent is negative 2.4, and the argument that it equals is that. Wow, man, that's easy to solve. I do need to type that on a calculator.
Yep, type it on a calculator.
So, because I need to figure out what that is. So let's pull up the handy dandy machine, turn it back on, and let's see. 10 to the, oops, that didn't work. Gotta use a little caret. Negative 2.4. Now make sure you don't use that minus sign. Don't use this subtraction symbol.
Yeah.
Because the calculator is not capable of handling that. So it looks like 3.98 times 10 to the negative third. 3.98 times 10 to the negative third. 3.98 times 10 to the negative third.
There you go.
Okay. A little scientific notation there for you. And you can do the same thing with the other one. And I'm sure you'll have a question like that in your math Excel. What are their hydrogen ion concentrations? Okay, we got that part. That's part A. How many times greater is the hydrogen ion? Oh, I guess I got to do the other one. Daggone it. Alright, so I got to do 8.4.
In the words of the great Mater.
So,
In the words of the great Mater. Tomater, that is. Daggone.
So we're going to go through the same process. Obviously, the first step would be to divide by -1. And
Man, let's skip ahead. Because you're just doing the same thing, right?
I don't know.
Alright, so we end up with that. 3.98 times 10 to the negative 9th.
Okay, so that's the other one. Now, see if I can answer their question. How many times greater is the hydrogen ion concentration of the vinegar than the baking soda?
Oh, so we just divide them. And without yawning, come on. Nobody likes to hear you yawn.
So,
in fact, they're all wanting to punch the screen right now.
8 times 10 to the negative third, or 3.98 times 10 to the negative 9th. Okay, well, obviously that's going to cancel out, become a 1.
Yes.
And I did see in Math Excel that when they did this question, they did want 1.0 times 10 to the power.
Interesting.
And when you take -3 and you subtract -9, you do get 6. Okay, so that's the answer to the question, including what they'll expect in math space. Math space.
Math space.
Math Excel.
Whoa.
Slip of the tongue there, folks.
Yeah, no kidding. That's going way
by
back.
how many orders of magnitude do the concentrations differ? Well, remember the orders of magnitude would be
6.
This.
Yeah.
Okay, so, orders of magnitude. Can we do that? Orders of magnitude. Or would it be pronounced
Yes.
Okay, in this case would be 6.
6.
Here. Newton's law of cooling. This is another science example of an exponential function this time, not a log function, but an exponential function. An object that has been heated.
Okay. Do not panic. you are not being asked to memorize Newton's law of cooling, okay? If you need it, you will be given that function on a test, all right? Along with a description of every one of those objects so that you would know how to use them, okay? Anyway, just thought I'd let you know so you're not panicking.
Will cool to the medium in which it is placed in, all right? So, you know, if you have a cup of coffee and it's in your kitchen, the air temperature of the kitchen would be the surrounding air, and it has a particular temperature. Typically, the coffee's hotter, so it's cooling to that temperature, okay, coming down. It says an appropriate value of K, and that K would belong to that particular situation, or, that coffee, that liquid, or whatever, the medium the object that you're cooling.